There's a couple different ways we can start. We can look at formulas or particular problems or answer questions that people have. Are there any preferences or things you want to see? Yeah.
I want to do the formula.
You want to do some look at different formulas? So, right. So one thing we can do is within that, kind of motivated by some of the problems that were on the study. So in the so these are the solutions that are there for some of these practice problems. But one of these problems, well, I'll see like that. They had this band-mounted video technology, so I did on a number of cracks and highways, and so they're driving on highways.
Sorry.
And there's no problem. And they made 8 sections, 50 meters long. They found an average of 22.1 cracks, standard deviation of 0.105, and there's a recommendation that you not get more than 0.1. So out of that, this is form of 95% confidence for the average. So it's kind of cluing you in that it's about averages. So one type of problem is when you have one sample, you're interested in average or mean, and it gives you the sample size, it has to give you an average and a standard deviation. And the population mean is in symbols is mu, and so we can do 95% confidence interval for the average. Say, and that's with this we use degrees of freedom to -1. We use the key distribution with that many degrees of freedom, and so we would have x bar plus or minus a t-value in our tables. Right? We would look in the 0.025 column, that degrees of freedom to get that cutoff, because the 95%. Look at the 0.025 column on the t-table. And then the standard error is S over the square root. I'm going to be 95% confident that the average value would end up in that. Would be covered by that interval. Yep.
When we use t versus when we use x?
Versus like a z, like
Z,
a normal.
yeah, sorry, z, that's what I meant.
So, most of the time in real applications, you don't know the standard deviation. So primarily, if it's averaging about a mean, and I'm giving you a standard deviation, then use that one. So we'll focus on that. If kind of in the early parts of the book where they talk about confidence intervals, say, well, you have a very large sample, and pretend you know the standard deviation instead of estimating it. Even if you estimate it with modern computers, you can get several decimal points. It's a little wider, so I think that's better practice. Yep, right. So the other way to do it is about hypothesis test. The mean equals some value versus an alternative. Say that it does not equal that value. In that case, it was 0.1 cracks per some distance. Right? In this case, we're going to generate a t statistic, x bar minus mu sub 0. How far is our sample average from this hypothetical, hypothesis value? We standardize it by the standard error, S over the square root. And if this t statistic value is more extreme than a t value, it's two-sided, it can be either positive or negative. So we will reject the null hypothesis if the absolute value of this t statistic is bigger than the 0.025 tail cutoff. And that would be the procedure using an alpha 0.05 level test. So primarily, I'll ask about 95% confidence interval over 5% tests. There might be an interpretation, you know, okay, the 99% confidence interval would be a little bit wider. That's not necessarily worse, it's just wider. Yep.
Okay, so just, this is like probably personal to me, but like, are you going to always give us the standard deviation, or are you going to ask us to find the standard deviation on some of these?
So in this case, now, you know, on the first exam, we included something with descriptive statistics. I was just calculating from data, but I'll give it to you for this exam.
Okay.
Right. So it will be written in the statement of the problem.
Okay.
Right. Like this one. In 8 sections, they found an average of 0.25 cracks with a standard deviation of 0.105. So that 0.105 standard deviation comes from those 8 sections, and that's the sample one.
Okay.
The one variation on this, that's very similar, but is a matched pairs study. In this case, the design has two variables, and they're measured on in pairs. We take the differences, x1 minus y1, 2 minus y2, and you know, it'll be one of the variables minus the other one. Then, you know, x of n minus y of n. We have n pairs. We have an average difference, the standard deviation of the differences. And so you could do a 95% you know, confidence interval for the average difference. So if we want the average difference, which would be the average of the x minus the average of the y. I wrote it x minus y because I wrote differences as x minus y here. Just you do it consistent, whatever, however you set it up. And then the formulas look very much similar to that other one. Yeah.
Does it matter if you do y minus x or x minus y?
If for most purposes, well, yeah, I mean, you're either going to get a positive or a negative, and then you just have to interpret in that context, right? If the average value of x is bigger, then these are mostly going to be positive, and so the confidence interval is mostly going to be positive, and you say that the average difference of this one minus that one is positive.
Okay, so how can we, like, what are some words we should be looking for, or like other indicators that this is a matched pair study
Yeah.
versus a regular?
Right. So what were some examples of words that we use for matched pairs? I mean, I could tell you that there's n subjects that are measured at time period 1, time period 2. Same people are measured 2 times, right? A before, after type of thing, right? Twins, right? And they're together. But in general, if you know, you could have one person in a medical study, and then they went out and found a similar person, and then for that pair of people, they flipped a coin, and one got treatment, one got control. So there'd be some fairly explicit description of how these pairs are done, or how they say the differences of measurement 1 versus measurement 2. And, I'm not positive if there's an example exactly like that in there, but it would be that pairing. Oh, the last one in the study problems was described as a pair. Does not look like. So these are the study questions. The last one that's in there, let me just bigger. Where is that? There it is. That's probably big enough. The last one that's in here, 10 women not on oral contraceptives had their systolic blood pressure measured at baseline. After duration of time on oral contraceptives, the women had their systolic blood pressure measured again. The average change was 4.80. Standard deviation was 4.566. So it's the same women, and it's clearly indicating change. Once you get that difference, and you have one sample, it looks very much like the other one. 95% confidence. 95% confidence here. Right, then the 0.025 and n minus 1 degrees of freedom, and the standard deviation of that change over the square root of n For hypothesis testing involving this, it's basically the same as that, but often the difference of interest very well could be 0, right? No change, versus an alternative that it is not equal to 0. And then our t statistic for testing that is the average difference, technically, minus 0, divided by the standard error. And again, you would reject that if the t statistic value is very extreme.
So a t-stat was either larger or smaller?
Yeah. Yeah. So if it's a two-sided alternative, and I'll phrase them as two-sided alternatives, so we don't, you can just do that, yeah.
Okay, so with the null hypothesis,
Uh-huh.
is it always the null hypothesis there's been no change, or can it be less or more?
Well, so if say you had a new drug, right, and the old one did an average decrease of 10, right, dropped blood pressure on average by 10. You could say, is it the same as the old drug? And now we have like generic variety, is it the same or not equal? So you could have 10 here, right, and then you would subtract 10 if
But
so
it's
equal
usually
to-
going to be equal to one some number.
Yeah, yeah, mostly it's phrased like that. Yeah.
Okay.
Yeah.
So you said that you reject if the t-stat value is too extreme.
Mm-hmm.
So
this
how much
is-
is too extreme?
So we're going to reject H0 if the absolute value of this thing is greater than this cutoff value.
Oh.
0.25 minus 1. So in that example, this one had 10 women in here, so, and it's 10. Average change, D bar here, standard deviation is here. And this part, I can take a hypothesis test. I'd probably just ask you one of these. If I said, is it different? You could do a confidence interval or hypothesis test. If the confidence interval doesn't include 0, then there's an average change. If the confidence interval covers 0, so 0 is plausible, then they're not significantly different. Or you do the hypothesis test. So with 10 women, and degrees of freedom for this match pair is minus 1 and 4.9. If you look at the T table, okay. Okay, so let's go. Okay, so make it bigger, right? So at 9 degrees of freedom, we're going to look over here, 2.262. Right? So if it would be bigger than n equals 10 and degrees of freedom that is 9, using the 0.025, the t 0.025 for 9 was the 2.262. So if you got a result that was a t statistic of 4 or 6 or 8 or something, you'd hardly even need to look up the cutoff values because you know it's so far out, more than huge number of standard errors. If it's more moderate, you want to report to me the degrees of freedom, which one you're using, and that cutoff value. And if it's bigger, it's out in the tails. It's out in the extremes when you reject it.
So is that the p-value? Like when you look and find it
So
in the chart?
the p-value is going to be the probability you're beyond a certain value. It's a little hard to find the p-values exactly on the tables. So the picture of the p-value, here's 0, here's the distribution, that's t within minus 1. And if you get a t statistic value, so this could be our d bar divided by s over the square root of n. Out here, the probability under that t value is a tail area. And that could be the p-value if we were just doing a one-sided hypothesis, but if we're doing really two-sided, so that equal distance away from the null is evidence against that. So the p-value would be 2 times that tail area. Right. And if that p-value is bigger than 0.05, then we don't reject. If the p-value is less than 0.05, that means that we're out here a long distance, we have a little tiny area out there, and then we reject. The null hypothesis is if the p-value is less than our alpha 0.05 level. Otherwise, we don't reject. And that's equivalent testing, like having some cutoff value, right? The t 0.025 tail, right? If you're beyond that, you're going to get a p-value that's small. And otherwise,
Could we go over 3A real quick?
3A from this.
That's the one talking about the proportion of trials that are
Oh,
reversed
yeah.
versus
So-
not.
Yeah, we'll do that one. We'll do that one. Let me mention one more formula.
Oh, sorry.
No, that's good. We will do that one, right? So the other way we get T problems, right, is if we have 2 independent samples. And we're comparing the means. So this one is a little bit more verbiage to set up, because you need 2 groups. So you need 2 sample sizes, or at least it has to tell you you have a certain number per group. You need the averages in the 2 groups, and the standard deviations in the 2 groups.
Was this the one where you have to like either pool them or not pool them?
Yeah, either pool them or not pool them. So on the homework, some people used pooled, some didn't use pooled. Following in the book, some people looked up, calculate like that bigger formula for degrees of freedom and things like that. So, so I graded it as correct as long as you were following along and following the formulas in the book. I prefer to pool them. I think it makes more sense. So I'm going to average the variances together here, and then take the square root of that, and that's my pooled thing for the variance. And then I use degrees of freedom for my T procedures. That is N1 minus 1 plus the N2 minus 1, so it works out to N1 plus N2 minus 2. I've estimated 2 means that's kind of using up information, so I get there. So for a 95% confidence interval, or for a 0.05 level test, I'm going to look up a certain T cutoff value, the 0.025 tail, based on whatever my degrees of freedom. And my confidence interval is going to be the difference between the 2 means, plus or minus a T value, 0.025, times the standard error. So there's the standard deviation, but you divide by the root of sample size. And in this case, there's 2 of those, and they get added together there.
So it's okay, you're not gonna ask us, are you going to ask us on the exam to do one pooled and one not pooled, or is it okay if we just do one or the other?
Just one of the others, fine. Given the time constraints, you'll probably only get 1 2-sample problem.
Okay. Awesome.
So I know you're gonna spend a lot of time studying all these different varieties. I can't ask you about all of them. Some of them might come back on the final. So. Anyway, that's that, the hypothesis test.
I'm not the best at the non-pooled, so I asked.
That they're equal averages in the group versus 2 differences. Then the T statistic that you calculate is x bar 1 minus x bar 2. Technically it's minus 0, but let's just leave that out. And then divided by a standard error, which is the same as that standard error formula there. And again, you get to have a sheet of formulas, so you can write these things down. You can write it down with numerical examples if you want.
So, Professor, When an example, like to make sure, I'm just being very explicit here, so I don't get the paired versus not.
Yeah,
But this would be like two entirely, like if it was for a drug, for instance, or to treat like a disease like diabetes, this would be like two entirely different treatments for that, like
Yep.
metformin versus dietary change, I think
Right.
is one that we
And
did.
so people that are randomized to these two separate groups, there's two independent samples, right? So there's no taking a difference between pairs, matched pairs in any way, right? So the problem 7 from these examples set up something like that. I wanted to rub it on the screen to get a bit of that, but kids that grew up with touch screen, it's like everything that they think is, they can touch everything and make it work. And so it's like, no, that TV's not a touch screen. You can't do anything.
You know, have you seen like apparently that's happened with books too, like that like kids will try to be
Yeah,
like
they kind of
this.
default, you get so used to doing something like that. Right? So this one, a study of reading comprehension study 3 methods of instruction, pre-test scores compared to the 3 groups. So it's just pre-test scores. The table below reports the average and standard deviation of the pre-test scores, reading scores for the 3 groups. So we have 3 groups. Sample sizes, 3 averages. And we concentrate only on the basal and strat groups. These two, actually 2 groups, 2 samples, 2 averages, 2 standard deviations. Compute a pooled estimate of the standard deviation. So that one tends to do it explicitly to test whether there's an average difference. Right? So the fact that it gives you 2 averages, 2 standard deviations, it doesn't mention matching. There's no average difference. There's no standard deviation or differences, so it can't do it as paired.
Okay. Perfect.
Right, so if this t-statistic, like the others, is extreme, if it's bigger than the p-value, right, then we reject. So we reject H0. If the absolute value of that t-statistic is greater than our t-critical value. And this we're rejecting really at the alpha equal 0.05 level.
And if we're doing it at a different level, you're gonna tell us, right?
I'll tell you that, but the plan is just to have you do it at the 5% level. I might ask, like did some of the other problems, something about interpretation. What does 5% mean as a type 1 error rate? You know, if you do something, if you know, after doing a question, you know, part C might be, if you tested this at the 0.01 level, would that make it harder or easier to reject the null? Right? Yeah.
Just type 1, type 2. Type 1 is rejecting null hypothesis when it is true,
Mm-hmm.
and type 2 is not rejecting it when it's
No, not true.
false.
Yeah,
Okay.
yeah, yeah. So type 1, we reject the null hypothesis when H0 is true. And the probability of type 1 is what we call alpha, and it's generally set to a small value. We don't want to do that. And then type 2 instead is don't reject. H0 when H0 is false. Sometimes you fail to reject if you have a weak study, if you don't have big sample size. You might not have much power to reject, so even though it's not true, you have a small sample size, large standard deviation, you can't prove much of anything. So, yes?
Does that mean that, presuming you have a big enough sample size and that sort of thing, your probability of a type 1 error is 0.05 if you reject it? Would that mean that you have a 95% chance of committing a type 2 error if you don't reject it?
Not necessarily. There's not necessarily quite a direct trade-off in that. So the picture related to power, right? So let's say here's the null hypothesis. And this is the sampling distribution of X bar. So it's centered at u sub 0, and it's a standard deviation. We use that in the place of that. We kind of spread it out like a t, kind of scaled, right? And so we reject, right, when we're too far away. We're going to reject h0 if our x bar is bigger than the mu sub 0 plus a t value in minus, if I'm doing just one sample, it's 0.025 tail. Times s of this gradient. Or if it's less. So this is, we're going to reject down here, we're going to reject up here. Or x bar is less than u sub 0 minus that cutoff value. If you think about the t value being somewhere around 2, you know, if x bar is more than 2 standard errors above u sub 0 or 2 standard errors below u sub 0, then it's kind of out there. And then, so alpha, right, we choose it. We choose 0.05. That determines the rejection region. Yeah.
That's your confidence interval.
Yeah, that's the width of the confidence interval. Yep. And then, if the alternative really were out here, right, the probability of a type 2 error really depends on, you know, where this falls. As I've drawn it here, we're in a pretty good situation, right? Because the rejection region, we reject, this is the probability under that thing. The chance that we're in the rejection region, given that alternative, that's a pretty low error rate. The kind of this tail up to about here, well, we also reject down here, which is almost 0. But that's kind of the error rate of type 2. If those two have been closer together, we're going to fail to reject more often, and that's not good. If they've been farther apart, we're almost certain to reject, and then that error rate's real small. So the alpha, you can set alpha to be 0.05, and depending on the setup of the problem, you can get any different. Generally, if you get bigger sample sizes, and these things get narrower, they're kind of relatively farther apart from one another, and you get more power.
So on type 2, you want that area to be small.
For type 2 area, you want this to be, would be like this little beta area in here. You want a very small chance of having that. Yep. You want the curve separated, right, in terms of relative to standard errors. So those are the T procedures, things for beams.
So one last thing, can you just
Sure.
explain power a little bit more? Because I'm a little confused what that is still.
So power is really the probability that you reject null hypothesis if H0 is false. You're trying to prove something and trying to reject a null hypothesis.
Oh, okay, I see.
And H0 being false is we make some specific choice for calculating it. And so the power, this is 1 minus the probability really of that type 2 error. And the type 2 is that we don't reject if it's false. That's sometimes written as beta. We did do a little bit of calculation with that. The plan for asking about it, rather than just kind of doing a calculation straight off the bat, would be either to probably do a hypothesis test first, and then say, would your chances of success go up if you had a bigger spread, smaller standard deviation, larger sample size? How would things play out there?
Okay.
I guess I could mention one other related point, sample size. Is when we did the one sample, that's x bar plus or minus a t value times s over the square root of n, right? This was called the margin of error of x bar around its average. And if we wanted a certain width, which would be plus or minus would be 2 times that margin. If we want a certain margin, we can set that thing equal to the 2 times this t as opposed to demand. Well, for planning purposes, we don't necessarily know the sample size. So people often guess sigma, or maybe estimate it from a small pilot study or based on general knowledge or things like that. And for planning, they often use, they set the margin equal to a normal value, sigma over square root of n, for planning purposes. So maybe use 1.96, maybe you could use 2 as a compromise. And you square both sides, m squared equals z squared, sigma squared over n. So you can solve for n. So this sample size formula gives you z squared, sigma squared over n squared. So if 95%, we use 1.96. If sigma, say, was a standard deviation of 25, and we wanted our margin of error to be plus or minus 5 units, whatever it is. Say this is a standard deviation of 25 pounds, this is a margin of error of 5 pounds. We want to know the average value within plus or minus 5 pounds. And then this would be 25 squared over 5 squared. So that's 25, it's about 100. Approximately, right? It would suggest that we would need that, at least that sample size to get that accuracy that we would want. Right? If you wanted a smaller margin of error, if you want to cut that in half, that multiplies the sample size by 4. If the population were more diverse, and this was 30 or 40, you'd have to have bigger sample size to get accurate.
Sigma indicates an average.
So this is like a standard deviation of the measurement. It's kind of the corresponding thing of the sample S.
All right,
Yeah.
so this is actually like, so with the actual, like I did that on 96,
Okay.
0.04.
Okay.
Now with that, would you round that up to 95 because you need to or 97 because you need at least that many to have that margin, or would you round it down to 96 because it's closer to 96?
Well, I mean, I think the safer thing is to round it up,
Okay.
err on getting a little bit bigger sample size to try and do that. Now, a lot of things are going to affect your study. You're going to actually get, a sample standard deviation. You're probably going to use t that's a little bit wider. So you could use that as guidance. 96, maybe round it up to nice 100. That seems like a nice even number.
So if we were to do this on the exam, would you want us to put down like our exact answer, or would you like?
Yeah, so if it came out to 96.04 and you said, 97, round it up, take at least that amount to try to get that. Because the goal is to get an interval a certain width that has at least 95% coverage.
Okay.
If you cut it back to 96 and round down a little bit, you might end up a little bit wider than you hoped. Right, so it's better to go up a little bit for accuracy.
And you'll give us sigma, right? In this case?
In this case, yeah, there'd be some indication. So some of the homework problems said, assuming that they had a number, I think 320 was one of the numbers, assuming you had the standard deviation, it was very close to the sample one. Right? Or if we had a sample one from a problem, you could use a number like that.
Okay. All right.
Right. So the other two testing situations and confidence concern proportions and one sample or two samples. In one sample situation, you're told a sample size, and you're either told X, the number of cases out of N, or maybe a sample proportion. You probably get NX or NP hat. You don't necessarily get both told to you, right? A confidence interval, 95% confidence interval for a proportion is our sample proportion plus or minus 1.96 p hat, 1 minus p hat over n. Square root of all of that.
proportion is basically the same thing as your, almost like the same thing as if you're doing an average, it's just slightly different.
Yes, we do use a normal, we do use a z-value here. And instead of having, s over the square root of n, like we did for one sample t, we have, this could also be written as the square root of t hat 1 minus p hat over the square root of n. So in this particular case of the binomial experiments, we don't have an s, we don't have standard deviation measurements. They're all 0, 1, success or failure. But the formula works out to be like that. So sample size figures in, the square root of sample size affects accuracy just like in both cases. But you do that version. Yep.
So in the book, when they give the formula for the confidence and the proportions, they give they give that one and also like a much more complicated one.
Right.
And they say to use that one for very large sample size. So people just use that one.
Yeah, well, we can use this one for that. Right?
Okay.
So kind of the modified formulas are trying to get a little bit more accuracy in the proportions or the coverage. So it's relevant. You could use it. I think this one is the standard
Okay.
one that I would see people use. Beyond that, there are something called exact procedures, where you figure out what's the lowest p that's consistent with your data and the upper p. So there's things called the exact binomial intervals or confidence intervals. And more or less there's a search for values of p that give you the lowest and highest consistent values. So there's a couple ways of doing it if you have real small sample sizes to get intervals. We focus mostly on this thing, right? So if you wanted to check, does the assumptions behind this, we do want a binomial type of experiment. We do want independent trials. We do want a constant proportion. So, maybe a part C of a question would ask about interpretation. If we find out that they had 2 people per household, or there was, that there was, 64 guinea pigs, but they really were in litters of, 3 to 7, and then asking about some, then they're kind of correlated and not independent anymore.
So this is, you could only really do this if they, you're kind of presuming that the subjects are independent of one another?
Yes.
Okay.
I mean, if they're dependent, then the binomial probabilities and the standard errors, these standard errors don't quite work. So if they're dependent, they might be more likely to be all large values, more likely to be all small values. So back in the 1800s, when families regularly had 10, 11, 12, 16 kids, people kept track of how many boys and how many girls were born in families, right? And so it looks like, looking at those data, there's a little bit of extra variation. Some families tend to have more girls and some tend to have more boys, and you would just based on a simple binomial. So there seems to be a little bit of association with exactly the biological mechanism. I don't think anybody really knows, or at least I don't know. Haven't heard that. But in any case, so if there's some way that the trials are not independent of one another, it kind of changes the standard error. We wouldn't use these, but it fits a whole lot of conditions. If we would generally want the n times p to be bigger and n times 1 minus p. We don't want to be too close to the edge. We don't want real small sample sizes. We don't want p very, very close to 0 or 1, because then the normal approximation of binomial doesn't work. One way of checking it is looking at the sample size. Some people say that this has to be greater than 5 and this is greater than 5. Or some people put 10 in there, but kind of just checking that it's not real small is good.
Would you throw a curveball at us like that of trying to do one of these with one of those assumptions being off, or would it more be what assumptions would be needed for this study?
So it could be asked, both ways. We don't have, we haven't studied a lot of alternatives to do when it's really small. So it's a little hard for me to if it doesn't really fit the assumptions, to say, do it a different way, because we really haven't done that. But, you know, say n was 200 and we were fine. Now somebody wants to replicate this, but they're only get n equals 20. Is there any problem with using this method if n is only 20? 20 is pretty discrete, it's not very continuous, so normal doesn't work quite so well for that. So it might be kind of a follow-up to it, but most of the problem should give you a way to do what you have there. Related to that, this one's amenable as well to a sample size formula. If the margin is 1.96, and I'm just going to write P1 minus P over n in here, you square both sides, m squared, 1.96 squared, P1 minus P over n. Solve for n. N is 1.96 squared, and P times 1 minus P, and then the margin squared in here. So typically, you know, this P times 1 minus P is the biggest when P is 0.5. If we want a margin plus or minus, say 0.04 for a confidence interval, you could plug those values in there and get a sample size.
So I remember one of the homework questions said something like, disregard P, and you told me to use the highest P. Like, would that be like something?
This is the high, yeah, this is the one that makes it the biggest.
Like, is that wording we should look for? Of like, oh, or should we just say if a P value isn't given, that we should?
You know, if it had an initial sample size and it said the estimate was 0.35.
Mm-hmm.
Unless I say something like be conservative and use 0.5 or use the value as the maximum, you know, and the sample probably had 0.35, you could, you know, say that was a first study or a pilot study, you could go ahead and plan it. You could put 0.35 and 1 minus 0.35 in here and get a sample size.
Okay.
So that would be irrelevant. One sample things, erase this, two sample things. You could do a hypothesis test. Is the proportion equal to P0 versus is it not equal to P0? And then we calculate a statistic, compare our sample proportion to that one, and divide it by P0, 1 minus P0 over n. Same kind of standard error formula, but under the null hypothesis, we use P0. And we're going to reject the null hypothesis if our z statistic is greater than 1.96.
P0 is the sample proportion, right?
P0 is going to be the hypothesis.
Hypothesis proportion, okay.
This p hat is the sample one.
Okay. Okay.
So that's one proportion, right? So there's that question 3 that you were asking about. That's question 3, right? That had some of these on here. 678 federal civil trials recently tried in front of a judge and then appealed 139 versus. Form a confidence interval or do a hypothesis test about this situation. So that's all it has to tell you, right? So it tells you n, it tells you x. So p hat in this case is going to be the 139 out of 678.
And you,
And here's the sample size one, right? One wanted to repeat the study and achieve a margin of error plus or minus 2% for an interval. Then our sample size would be a z value squared. You could use that p hat if you wanted. You calculated that. That's about a fourth, I guess. Something like that. You could use that one because that's based on some data and that'd be kind of realistic. Okay. And then 0.02 is the margin.
Okay.
So dividing by 0.02 is like multiplying by 50. So 50 squared is 2,500, so it's already pretty big there. This is like 2, right? If is 1.96, times that's 1/2. Well, yeah, so it's, it can be, hi, there.
Sorry, so
A few of those, thank you very
Sorry
much.
about that.
That's all right.
Have a good one.
Yep, thanks. That's for the biostatistics class. Few homeworks. Any questions about formulas for? Last one. All right, we have two proportions. You have two sample sizes. You have two counts, or you have two sample proportions. And 95% confidence interval for P1 minus P2, P1 hat minus P2 hat, plus or minus 1.96 value, and then the standard error of the difference. So the P1 hat, 1 minus P1 hat over N1 for the first sample, that's the variance of the estimator for the first sample, plus the variance of the estimator for the second one. And that's the 95% confidence interval. Hypothesis test, they're equal versus they're not equal. Because they're equal, we're going to take a p hat that's, if they really are equal, we want to put all the data together and estimate that one thing, x1 plus x2 over n1 plus n2. And then we calculate the z-statistic, the difference of the two sample proportions. And then we have p hat, 1 minus p hat, and we divide that by n1 for the first sample, and we divide it by n2 for the second sample, and take the square root of that whole, that variance. And that's our statistic there. And we would reject the null hypothesis if that's bigger than an absolute value of 1.96 again. Those are confidence interval hypothesis testing formulas. Yes.
Excuse me, so for proportions, you use the z statistics, and for averages, you use the t statistics
Yep.
usually? Okay. And one last question.
Yes.
Actually, that's a lie. It's probably gonna be like the 20th
Next
and last
question.
one. Next question. So we're going back to homework 4 for this exam, or are we going back to homework 5?
Homework
Okay.
5.
Because like, I was wondering, this is all about like hypothesis testing then and that sort of thing. And we're,
Yeah, so there was a little bit,
because we're not talking about like discrete variables in this one.
so homework 6, right, if you look at homework 6, it had some part on chapter 5, right? And that would had a little bit of discrete bivariate, right? So if you had a distribution of one variable and another variable, and maybe this has 3 levels and this has, 2 levels over here, and you put in, you could be given probabilities. So that's 10% for this one, so it's going to be 90% for this one, and maybe 0.9 and 0.7, and then what is that going to add up to? So that's 10, 20, so it has to add up to 80, so 1.4. No, that can't be 1.4. 80, so 74. It should add up to 1. So 74, 81, that's 90. Or so you could have something like this. So there's 10% this row and 10% this row and 80% over here, right? Or something like that. So you can figure out the margins. Are these two things independent of each other? want the probability that of two values x and y, be the probability of the x values times the probability of the y values for all pairs. Now 0.1 times 0.1 is that one, and 0.1 times that one is that one, but in this row it fails. Like 0.1 times 0.1 is not 0.03. So the probability of 2 and 1 for x and y is 0.03, but the probability that x is 2 times the probability that y is 1 is 0.1 times 0.1, which is 0.01. So they are not equal. So they're not independent.
So how much of this stuff is going to be on the exam? Is it going to be still very little bit, or is it going to be like?
Probably one question.
Okay.
You know, I mean, if we're going to have 5 or 6 questions, kind of a 1 sample problem, a 2 sample problem for testing, a confidence interval problem, hypothesis testing problem. There's kind of this stuff with the discrete distributions, maybe an interpretation question. So it'll be there to some degree, right? Yes.
I was just gonna ask, can you quickly, I mean, it's a simple computation, but 4b, the p-value, can you just go through that very quickly?
So it's one of the 4b.
Yeah. It's just where you computed the p-value.
Okay. Right. So we can come back to this one, but look at number 4b here. So this one, right, was the 678 trials, 139 were reversed. So p hat 139 over 678. So it is, there it is, it's 0.205. Right. And a newspaper says that p is 0.24. So we have data, we're going to evaluate that claim. So is the newspaper right? Is it 0.24? Or is that not right? So the z statistic, p hat minus p0, and then we put the p0, 1 minus p0 over in here. This is p0, whatever the null value is there. So 0.205 minus 2.24. And this one's 0.24. 1 minus that is 0.76 over the 678. And this tells me the z statistic is negative 2.13. Right, so if you're doing a one-sided hypothesis, that's bigger than or less than negative 1.96. So we're going to reject H0 if, well, because our z statistic, negative 2.13, is less than negative 1.96. That corresponded to the alpha 0.05 cutoff. So we reject. If not 24%, it's actually a little bit less. And the question is, what's the p-value? Well, one thing you need to do is get the probability that a normal is less than the negative 2.13. Why are we doing that? It's the p-value is what's the probability we're as extreme or more extreme. So in this case, since it's low, what's the chance we're less than that? So it's that tail. What's the chance we're less than 2.13? You'll get the normal table and the t-table, like the book. This is. And then if I gave you just half the table, 2.13, or 2.13 had this 0.9834 probability. So the chance that you're less than that, 9834, am I computing the right thing? 2.13 So here's 0, it's 2.13, there's 0.9834, is that what it was?
Wait, aren't we looking at negative 2 point?
It is negative. The tail area is 0.0166. If you had, that would be what would be left over, or the negative 2.13 is at 0.0166. Yeah, that's a probability for less than that. So that's 0.0166. What is the solution?
So you just multiply that by 2.
And multiply it by 2. Right. It's a two-sided alternative. If you made it a one-sided alternative, and you wrote it down saying that no, it's less than 0.24, then you can just give me one tail. Right? If you write it as not equal, then we just double it.
Okay.
As long as you're consistent with that, that'll be okay.
All right, thank you.
So with this, we're just returning to this. How else can you show these things are not independent? Well, you could say that the probability that y equals 1 is 0.1, whereas 2 is 0.9. But what's the probability that y equals 1 if x equals 1? Well, the probability that they're both 1 over the probability that x equals to 1 is that conditional probability. So that they're both 1 is 0.01, and the chance that this one is 0.1. So that's 0.1. That's no change. That's consistent with independent. What if probability that y equals 1 given that x equals 2? And that one would have to be unchanged as well. But when y is 1 and x is 2, that's 0.03. The chance that x is 2 is 0.10. Right, so that's 0.3. So y equals 1 and x equals 2. We're dividing by over the probability x equals 2 is 0.1. Yeah, it's 0.3. So that's not 0.1 anymore. It's changed. Right? So if they're changing, then they're not independent of one another.
If they're changing, they're not independent of each other, or
Right.
they are independent of each other?
They're not independent of each other, right? So it's as x changes, as you get different values of x, you get different probabilities for y. So x is affecting y, and they're not independent. They're dependent on each other.
That kind of makes sense.
But if I tell you something about one variable and it's going to change your probabilities for the other one, they're dependent. They're influencing each other. Changing the outcomes. Any other?
Wait, can you say that one more time? When they're changing, they are then.
So if two variables are independent, if x and y are independent,
Okay.
yeah, then the probability of them together is the probability of one times the probability of the other. As well, the probability that x, given a certain value of y, conditional probability, put all of this together, what is the probability of y? Well, if they're independent, right? If they're independent, then the numerator up there splits into the two pieces, and the y parts cancel out, and you're just left with the x parts. So independent means that whatever you know about y doesn't change your x probabilities. So that's most of the time. So, when you get the problems, you can write down partial solutions, you can write down formulas, you can identify the different elements of the question, where's the sample size, where's the average, and things, and, write out and show work. And, give you those couple of tables and, one of your calculators. And
Thank you.
Professor.
This weekend was insane for RA things, so I will get you the homework hopefully by tomorrow, because just yesterday was insane. Or like last 2 days were insane, because like literally one day I was dealing with a sick resident, and the next night I was in a program that I had that was required. It was insane. I'm sorry.
Well, sit, give me what you can.
I will.
No, I'll give you that. Thank you very much.
Well, I worked 9 hours yesterday as well. I wish I could do it. I just want to see something.
Yeah, most of
This like, put your nose in a book and like, absorb your hello.
Yeah.
Kind of like, you need some of the thing in the library, right?
It's just nice.
Or the- yeah.
Oh,
one for each class, so like,
It's how we.
I'm struggling,
yeah, no, I didn't check completely, but could you send me a note about that? That'd be great to have a reminder. I'll write it down. You want to redo those two, that's right, so why don't you redo that section and write out the solutions to that? Yep. Yeah, why don't you do that? Can you bring it, can you just bring it to the exam on Wednesday? You have time to look at it? So that would be great. Yeah, thank you. Yeah. Yes.
Have you been, or has my coach?
Yes, I got an
Okay,
email
Cool.
from him, and then I'll get it, it'll be written pretty soon, and so I'll.
No worries, I just want to make sure that he
Yep.
was.
Yeah, no, he sent a nice email and was clear, everything.
Perfect, all right, thank
That'll
you.
work out.
See you tomorrow.
Yep.